In this video, I'm going to give information about nonlinear vector fields in the plane. What I mean by this is, well, let's consider a dynamical system. X dot equals f of x and y, and y dot equals g of x and y. Or we can write this as, say, a vector x vector dot equals f of x. Depending on well, just what kind of mood we're in, we can use either system of notation. Now, most of what we did for dynamical systems on the line carries over to the plane. So here we go. A fixed point is a constant solution. And it's found by solving. We'll now have a system of equations. Little f of x and y equals 0, and little g of x and y equals 0. Now we have linear stability analysis. So suppose that well, let me tell you, let me think here. Let me use, now I don't know if bars are going to work either. Let me call it x hat and y hat. So suppose that is a fixed point. Now I'm going to let x equal x hat plus u and y equal y hat plus u. So u and x, oops, that should be a v. So u and v are functions of time t, just like x and y are. So now if I start with the equation x dot equals f of x and y and fill in, well, x dot is the derivative of the constant x hat plus u. So x dot is just u dot. Then over here I have f of x hat plus u, y hat plus v. At this point, I'm going to use a Taylor expansion in both slots of f. So what that is going to do, first let me do it in the x slot. Okay, so in this equation, never mind this part. This part is simply fed into f as usual. I'm assuming that u is small, so assume u and v are small. So we're interested in behavior of the vector field near the fixed point, which means that I'm going to be interested in this first order expansion. And what you're seeing here is entirely analogous to what in one, let me use a different color. In one variable, it would look like f of x hat plus u equals f of x hat plus f prime of x hat times u plus, and then this one is easy to continue. So that's essentially what I've done here, just focusing on the first slot of f. I need to do the same thing, but for the y slot. So here we go. First, I'm going to expand here. In fact, why don't I do that in a different color? Let me see. Let me do this part in green. So that'll be, now I leave the x the same and expand in y. Oops. So that's an expansion there. And how about, let me expand this one on the next line. So that's sub x of x hat y hat times u plus f sub x. Oops, that should be a v. No, that's right. No, I know what I need to do. Let me do this. I'll put the u out here on the end. Okay, let me make some space here. Okay. By the way, the thing that you're seeing here, that means terms that are bounded in magnitude by u squared. So in other words, some kind of correction that is less than or equal to some big constant times the absolute value of u squared. And the big O of v squared is the same thing, but it's a correction that's bounded by some constant times the size of v squared. Okay, so when you put all of this together, we get u dot equals f of x hat and y hat plus, I'm going to write f sub x of x hat and y hat times u. That's from there, plus f sub y of x hat and y hat times v. That's from there. And then everything else has either a u squared or a v squared, or there's going to be one term here that has a uv. But at any rate, all of these are on the order of, say, u squared plus v squared. Okay, so that's the Taylor expansion for the x dot equation. And since we're at a fixed point, f of x hat and y hat is 0. If you do the same expansion for g, well, what that means is that we go back here to this equation, y hat equals g of x and y, and substitute that offset form again. Assume u and v are small, and now we do the same thing for the two slots in g. Again, oops, we'll get this time, everything should be at g this time. X hat, y hat, plus g sub x of x hat, y hat times u, plus g sub y of x hat and y hat times v, and the remaining terms of the expansion are quadratic, or at least bounded in a quadratic sense. And again, since x hat, y hat is a fixed point, g is 0. Okay, so let's now put all of this together, write it neatly. So f sub x times u, f sub y times y. And I'm just going to write here higher order terms, HOT, and v is something similar. Oops, g sub y times v plus higher order terms. So this is a set of differential equations for the offset from the fixed point. So essentially here is x hat, y hat, and then if we start over here, uv is that arrow, and we want to see, well, does uv flow away, or does it flow back toward the fixed point? Does it arc around? Does it spiral in? Or does it spiral out? So there's all these possibilities for what might happen. And to determine which one actually happens, here's the nifty thing you can do. You can stack these, let me go ahead and write this as ddt. You can stack these equations into a column vector. And if you look carefully at this, that can be written as a row of a matrix times a column of u and v. So f sub x of x hat, y hat, and f sub y of x hat, y hat. So that row times a column of u and v. The second equation can also be written as a row of a matrix times u and v, and that's g of x, x hat, y hat, and g of y, x hat, y hat. And in fact, you should recognize that this is the Jacobian matrix of the vector function f of, let me write it like this, x and y is xy and g of xy, evaluated at xy equal to the x hat, y hat. That's the fixed point. This big matrix is a constant. So we've essentially reduced the question of what happens near the fixed point to analyzing the behavior of a linear differential equation in the plane. So this is called a linearization about the fixed point. Okay, so here's the important result. So suppose A is equal to this Jacobian at the fixed point. As long as the eigenvalues of A satisfy that the real part is not 0, the behavior of the linear system given by this equation accurately reflects the behavior of the nonlinear system in the vicinity of the fixed point. If you really want the details, this is something called the Hartman-Rodman theorem. And there's a good bit of theory that goes into proving this, and I've stated it informally. But this is the key intuition to this result. Now, some terminology. If all eigenvalues of A equal to the Jacobian at a fixed point satisfy that the real part is not 0, then the fixed point is said to be hyperbolic. I am not sure of the origin of this term hyperbolic because there may or may not actually be any hyperbolas involved in the dynamics. For whatever reason, a lot of things in mathematics that fall into several different cases are divided into a hyperbolic case, an elliptic case, and a parabolic case. I have never heard of a parabolic or elliptic fixed point, however, so I don't know why we use the term parabolic or hyperbolic here. It's just math notation. What can I tell you? Now, there is also a notion of something called structural stability. So, in the neighborhood, so let me back up. Well, I guess that is as good a way to say it. All right, so in the vicinity of a hyperbolic fixed point, small changes to the vector field do not significantly affect the behavior of solutions there. So again, I will say this is structurally stable. There's, again, a lot of theory that goes into this that we aren't going to have time to get into this semester, but this is the key concept. Basically, these theorems and whatnot say that this linearization does accurately give us local information about what solutions look like near the fixed point, as long as none of the eigenvalues have a real part of 0. If there is an eigenvalue with a real part of 0, then things can get kind of crazy. I'll be saying more about that in future videos. But right now, this is the sort of key concept. You start with a nonlinear vector field, and you find the fixed points, and then you look at the Jacobian. That gives you this linearization near that fixed point. and then you do eigenvalue and eigenvector analysis to determine what that linear system does. And then that tells you very accurately what the behavior of solutions near that fixed point is. And so then you can start putting the pieces together. Now, let me give you a few more bits of vocabulary. The points that satisfy, oops, just one of the equations f of x and y equals 0, or g of x and y equals 0, these are called nullines, and they intersect at fixed points. Nullines can give you a lot of information about larger scale behavior of solutions to these nonlinear dynamical systems. And very often they're a lot of information, and they give a lot of information, and they're relatively easy to find. Okay, so with that, I'm going to end this video, and in a future video, I'll show an example of how to do this kind of analysis.